Okay, so now we're looking at hypothesis testing for a difference of means. And here we may want to compare two means from separate populations to see if there is evidence that they are the same. We proceed by assuming they are the same and then use the significance to see if we have sufficient evidence to support or not support our initial claim that the means were equal. Now, in matched pairs, we are looking at the mean difference for one sample data of the differences. For two sample inference, we are looking at the differences between the means. So it's still going to follow this phantoms model where mu1 is the true population average of, and mu2 is the true population average, and mu1 minus mu2 becomes the true population difference of means. We assume they're equal. We are testing one of these three claims. Here, we are checking our assumptions again, and now normally we will check the parameter instead of the statistic. This was when we were doing this for proportion, so I actually need to take this out. But essentially here, I'm not looking at large counts for the proportion model, but I'm looking here at one of these three conditions for normality. If these conditions are met, we'll use a two-sample t-test for the difference of means, which has the following formula. And notice if we assume that the two are equal, this just zeroes out. So really the test statistic is the difference of the samples divided by the standard error of the statistic. We do make sure that we note our degrees of freedom. We use one of the following probability statements to obtain the p-value. And if the p is low, we reject the HO or the null hypothesis. And if the p is high, we cannot deny. We fail to reject. And depending on which of these two decisions, there either is sufficient or there is not sufficient evidence to claim the alternative hypothesis. So another infamous example of a two-sample t-test comes to us from the 2010 AP Statistics exam, FRQ number 5. These box plots were not included in the original, but as you can see, we're going to need them for our normality check. And let's suppose that a large pet store buys the identical species of adult tropical fish from two different suppliers. We have Buy Right Pets and Fish Friends. Several of the managers at the pet store suspect that the lengths of the fish from Fish Friends are consistently greater than the lengths of the fish from Buy Right Pets. Random samples of 8 adult fish of the species from Buy Right Pets and 10 adult fish of the same species from Fish Friends were selected, and the lengths of fish in inches were recorded as shown in the table below. I have my sample sizes, my actual data points, their means, and their standard deviations. Now, do the data provide convincing evidence that the mean length of the adult fish of the species from the Fish Friends is greater than the mean length of the adult fish of the same species from Buy Right? So, let's go ahead and walk through our state plan do conclude model. And here, we have two different means that we're comparing. So, my first mean is going to be mu b, which is going to be the true average length or mean length of adult fish from Buy Right. From Buy Right Pets. So let's fill that in. From Buy Right Pets. Next up, our mu f here is going to be the true average length of adult fish from Fish Friends. And we're kind of cheating here with the shorthand notation, but if I were reading your work, I would assume, oh, this isn't an 11. I'd assume, oh, the true average length of adult fish from Fish Friends. Okay, so next up, what we'll do here is we need to identify our hypotheses that we'll be testing. Now, because we don't actually know the truth yet, we're going to claim that they're equal. We'll give them the benefit of the doubt. Maybe we just have some sampling variability going on and we just got a little bit unlucky. But we are testing the claim here that the mu for Fish Friends is greater than the mu of the Buy Right. And we weren't given a specific alpha level, so we're just going to use our basic significance level here of 0.05. So we've stated our parameter and what we are trying to test. Now, I went ahead and used the StatsMedic applet to graph this data for us, but if not, you could graph using a dot plot and just comparing the individual observations, which is actually what I did in my notes here originally, but I don't know, I have terrible geometric reasoning, so that's an example of a dot plot, but here we could use the box plot, and I'm just using this from the StatsMedic applet. Oh, I'm clicking out of my zone here. But Statsmatic is really awesome. It lets you graph these, and I'm about to sneeze. That was a gnarly sneeze. Glad you did not see that. But with Statsmatic, you can do box plots, you can do histograms, you can do a stem plot if you wanted to, or the dot plot, which I mentioned. But I went ahead and just took the snippet here for the box plots. Now, we have to check our assumptions to ensure validity in the procedures that we are doing. So, I have to check my 4 assumptions here. And we have the following. So, in my assumptions, the first one is that I had a random sample of 8 fish from Buy Right Pets, and then I had a random sample of 10 fish from Fish Friends. Next up is my 10%. Since I'm sampling here, this is not an experiment, but we're sampling, so I can assume there are at least 80 fish of the species at Buy Right Pets, and at least 100 fish of the species from Fish Friends. And the reason I picked those numbers is using the 10% condition. We're sampling less than 10% of the populations. It's okay. The degree of dependence becomes negligible. You can also write this out as an inequality. I just chose to spice it up here. Now, since the fish are coming from 2 separate stores, we can assume the fish length results are independent of one another. Because it's 2 separate stores, there's no way that one store would influence the length of my fish from a completely separate store. Now, I'll put the graphical display back up here, but since the box plots, or since the, you know what, here we go, since neither distribution of fish lengths reveals any extreme skewness or outliers, the normal model is appropriate. And since our conditions are met, we will use a 2-sample t-test for the difference in population means. Okay, now just to go back to this point here, is that here's my graphical display. When checking the graphical display condition, yes, there might be some skewness in the graph, but unless it's like completely tailed off to one end or completely tailed off in the other, we can assume it's mostly appropriate. So we can see the Buy Right data appears approximately symmetric, whereas the Fish Friends, if you look at the tails, could be skewed to the left, but if you look at the IQR, could be skewed to the right. We're just going to assume the skewness cancels out, and we'll have a relatively symmetric distribution here. So that's all I wanted to say on that one. And also for outliers, unless there's a dot, since we're using the modified box plot, unless there's an explicit dot that notes the outlier, we can assume that the normal model is appropriate because there's no extreme outliers or skewness. So now we've done our parameter, our hypotheses, our assumptions, and the name. Now we need to obtain our test statistic. So here, the test statistic didn't specify for us, so we're just going to go in order. So I'm going to take the difference in the samples here between Buy Right and Fish Friends, and I would subtract the parameter, but here, since we claim the parameters are equal, that the 2 means are equal, anything minus itself is 0. So it would just be minus 0 in the numerator, so I'm actually going to ignore that for now. And then I'll take the standard error of these differences. And of course, even though it's a difference, why is there a plus sign in my denominator? Well, because we know that when we combine the spreads of 2 different distributions, we can't have negative distance. We're just checking the typical distance of the observations from the new center. So that's why, again, just throw back 2 random variables there. But it would appear as though our Buy Right sample was 3.4 minus 3.46 from Fish Friends, divided by the standard deviation at Buy Right was 0.434. We'll square that and divide it by the 8 Buy Right fish. And then the sample standard deviation of Fish Friends was 0.55. We'll square that and divide it by the 10 fish from Fish Friends. Now, you'd totally do this by hand, but I am not going to do that. I'm just going to pull this from my calculator, but I got a test statistic of t equal to negative 0.2587, typically just using 4 decimal places here. And to find my p-value, it would look something like this probability statement, that our test statistic is less than negative 0.2587. And when I find that value, I get a rather large p-value of 0.3996. So actually, when I sample in repeated sampling of size 8 from Bi-Rite and repeated sampling of size 10 from Fish Friends, there's actually almost a 40% chance that the mean fish length is going to be greater from Fish Friends than from Bi-Rite. This is not a significant result. This is almost what we'd expect due to chance alone. So, in order to bring this into a conclusion, we will make a comparison to our significance level. So, since the p-value equals 0.3996, which is greater than alpha equal to 0.05, we fail to reject the null hypothesis, which means there is not sufficient evidence to claim the average fish length from Fish Friends is greater than the average fish length from Bi-Rite Pets. Now, what type of error is associated with our decision? Here we've failed to reject the null hypothesis, and if we failed to reject and the null hypothesis was actually false, this would result in a type 2 error. Now, so that's just an example of a typical inference question. And then, of course, if you did obtain a statistically significant result, could you claim that, what could you claim from that? This is a random sample, so we can generalize, we can associate, etc. So just some the procedure of a 2-sample t-test for the difference of means, but then also some follow-up questions for the procedure itself. Now, of course, in true Pinto fashion, go ahead and take a look at this example here, comparing educational achievement and salary achievement for different levels of degrees here. So we're looking at the difference between the master's and the bachelor's degree. So go ahead and conduct your test, and then we'll come back and review. And I totally didn't even tell you to pause the video and try it out. So maybe some of you just instantly went to this part. Maybe some of you are actually still working. All good. But here we define our parameters. We create the set. And notice since I'm looking here at the difference, I'm saying that they're just not equal. So I don't know if that difference is less than or greater than. I just care that there's a difference. We've got our random samples. We're sampling less than 10% of the population. Our results are independent. And now what I like about this problem is that there's actually 2 criteria for the normal model. And I did not use my degrees of freedom in the previous example. My apologies, but you will pull that from the calculator, so don't sue me. But here, for our normality condition, one meets the central limit theorem due to its sample size, and then the other meets the symmetric distribution criteria. So we're still able to proceed, but notice again, all of these conditions have to be met for both populations. Here we do our formula, and then of course, since I'm reporting the degrees of freedom from the calculator, I would give that out. I would use this probability statement here. Our rule of thumb, if it's a positive test statistic, use the greater than, and if it's a negative test statistic, use the less than. Just a general rule of thumb, or else you're going to end up with an extremely large p-value, which could lead you to incorrectly decide. And here, since our p-value is low, we'll reject the hoe. There's sufficient evidence to claim that there is a statistically significant difference between the means of those who obtain a bachelor's and those who obtain a master's. So that's going to actually bring us to the conclusion here of our inference for means. Tune back in a couple of units when we revisit means, but looking at the slopes. So go ahead and rewatch any videos that you still have questions on, ask questions in class or in the comments, and then that'll conclude our unit for inference for means.